The title is Query Lower Bounds for Correlation Clustering Under Memory Constraints. This is a joint work with Sumegha, Garg, and Periklis Papakonstantinou. Time-space trade-offs are believed to be very hard problems. It will probably remain open long after NP and P being separated. Specifically, we don't even know the separation between log space and NP. That is, whether set can be solved in simultaneously log space and polynomial time. So far, we only know of explicit problems that require either near linear space or slightly superlinear time. This is proven in the non-uniform Rand model by Bing, Zacks, Sun, and Wei, and in the Turing machine model by Ryan and Williams with a slightly better time bound. In this work, we study time-space trade-offs in the random query model, which is a query model introduced by Raz and Zhang in 2020. Well, algorithms in the classic query model have query access to arbitrary input elements. Algorithms in the random query model receive random queries that are uniformly random samples of input elements and their values. More specifically, for binary problems, the input is a binary string X, and each random query returns a uniformly random I from 1 to n, and the value of xi. In this work, we consider graph problems, where the input is a graph G, and each random query returns a uniformly random UV from all pairs of vertices, and an indicator of whether or not U and V are connected in the graph. So this is a clean mode of computation and is closely related to the Cuban collector problem. We choose this model because it is easier to study, and we hope lower bounds in this work we will inspire time-space trade-offs in stronger models of computation. In this work, we consider the correlation clustering problem, which is a discrete machine learning problem. In this problem, we fix an approximation parameter epsilon. Given input a graph G, for a clustering, which is also a partitioning utility set C, the cost of the clustering C is the number of edges between different clusters plus the number of non-edges inside the clusters. The cost of G is defined as the minimum over all clusterings, the cost of C. We consider two different versions of correlation clustering in this work. In estimating correlation clustering, the output is an estimation of the optimal cost to within additive variable epsilon n squared. In the recurring version, the output is a clustering itself, so that the clustering has a cost of that is near optimal to within additive variable epsilon n squared. So here is an example of the correlation clustering. So in this graph, lines represents edges and dashed lines represents non-edges. If we cluster 1, 2, 3 together and 5, 4, 5, 6 together, the cost is 3 because there are 2 edges that bridges different clusters and one missing edge inside cluster B. But if we cluster 1, 2, 3, 4 together and 5, 6 together, there is only one missing edge inside the cluster A and one edge between the two clusters. So our main results are 3 lower bounds to correlation clustering in different models and different settings. The first result is a lower bound in the adjacent matrix model for recovering the correlation clustering. We show that any algorithm that for recovering correlation clustering to within additive variable epsilon n squared requires n over epsilon squared number of queries. This matches the upper bound in Brizan, Cesak, Bianchi, Podisha, and Vitale. We noticed that the algorithm in the previous work also works in the random query model with the same number of queries. Our result 2, which is also our main result, is a time-space lower bound for estimating correlation clustering. we show that any algorithm for the seemingly easier task of estimating the correlation clustering under memory constraints may require even more than n over epsilon square number of queries in the random query model. As we noted, n over epsilon square number of queries is even enough to recover the whole correlation clustering. And we show that under memory constraints, we may even require more number of queries. In our result 3, we show a lower bound for recovering correlation clustering in a stronger model, where both adjacent matrix and adjacent list queries are allowed. We show that any algorithm requires n over epsilon queries in this setting. So here are previous results on lower bounds, on time space lower bounds in the random query model. In Raz and Jan 2020, they showed that any zero-error random query algorithm for computing a Boolean function of sensitivity k must have a time space trade-off of at least n times k. Later on, Dinur shows that any bounded array algorithm for Boolean functions requires a time space trade-off of omega n times if, where if is the total influence. So Rasenjan is achieved by a reduction to the coupon collector problem in the random query model, and Dinur is the result of Dinur is achieved by a reduction to the communication analog of coupon collector problem. But for approximation problems such as the one we consider in this work, the previous works do not directly apply because approximation problems tolerate approximation errors. And in this setting, no small set of input elements have a high influence. So here, to present our proof, we start with the adversarial input distribution. So this distribution will be used in both proving result 1 and result 2. We let distribution Gy, the ES distribution, to be the input graph G that we sample a hidden partition P first, where P can be represented by a lengthened binary bit string. And vertices labeled 0 are one part, and labeled 1 are another part. And for every pair of vertices UV, we connect them with probability half plus 10 epsilon if U and V are belonging to the same part, and with probability half minus 10 epsilon if they are belonging to different parts. We can also think of it as a noisy complete bipartite graph, where each edge and non-edge is flipped with independent probability half plus 10 epsilon. We also use Gn to denote the uniform Erdős-Levin distribution. So we start with the proof to result 1. We use graphs from the ES distribution. We first show that the hidden partition P dominates the optimal correlation cluster, which means that for an algorithm to output an approximately good answer, it has to learn omega n bits of information about P. But we also show that each query only reveals epsilon square information about P. That means that any algorithm needs at least n over epsilon square queries to output approximately good answer. Then we switch to result 2. As we already noted, the previous result already gives an algorithm that shows that n over epsilon square number of random queries are even sufficient to recover the correlation clustering. So our idea is to partition the T random queries into blocks of length 0.01 n over epsilon squared, where T is a desired tiny lower bound, and 0.01 n over epsilon squared is determined in a way that by looking at each block alone, the algorithm is not enough to figure out the answer. And then we show that algorithms learn little in each block. And we show using hybrid argument to show that if the algorithm learns little in each block, the algorithm also cannot distinguish the yes and no cases in the whole T random queries. In fact, this framework extends the classic Fourier analytic framework for proving sketching and streaming lower bounds for cut-related problems and matching-related problems. And it has been successful in massive previous works. But there are two main differences in our case, and which are also two main contributions compared to previous works. The first is that we work on dense graphs, where previous works work on sparse graphs. And the second is that we obtain a time space trade-off instead of space lower bounds in previous works. And due to the differences in the settings, our techniques are also different that we will introduce later. So to start with, so the proof starts by showing that the random graph G in the yes distribution and no distribution has a cost of gap 5 epsilon squared n squared with high probability. So this reduces the lower bound to showing the indistinguishability between the yes distribution and the no distribution. In fact, we will focus on the distribution of query transcripts, which means the string of queries and query answers. More formally, we let dyt and dnt to be the yes and no distribution of query transcripts of length t. We fix k to be the number of blocks, and we introduce intermediate query transcript distributions that we will apply the hybrid argument. For every L between 0 and k, we let dtl to be the distribution where the first L blocks come from independent yes distributions, yes graphs sharing a hidden partition P, and the last k minus L blocks coming from independent no graphs. That means that dtk is a distribution where the k blocks are all independent yes graphs that shares a hidden partition P. And we notice that this is different to the yes query transcript distribution, in which all the random queries are consistent to the input graph, and we capture the lower bound to algorithms for distinguishing the inconsistency between different blocks by introducing added lower bound in the same vector problem in the random query model. And we capture the indistinguishability between different pairs of intermediate query transcripts distributions by introducing added lower bound in the PDBHP problem in the communication model. So here we formalize and introduce the same vector problem. So here is a number capital N, which is n choose 2, and a number P between 0 and 1. And K is the number of blocks the device T. The problem is defined on k+1 input strings following the Bernoulli distribution of probability P. And you can think of that X represents a yes input graph, and the Y1 to YK represents the no input graphs in each block. And an algorithm for this problem needs to distinguish between the following two cases. In the yes case, there is a string of T random queries from X. And in the no case, the random strings, the string of random queries is a concatenation of K blocks of random queries from each of Y1 to YK. The lower bound we will prove is query lower bound of n squared over S, where S is the number of bits of memory. There is a trivial matching upper bound that the algorithm only needs to remember the first S random queries, and will check whether the remaining number of the remaining random queries are consistent to the first S queries or not. So here is our proof sketch. We assume an algorithm with S space that makes T queries. And before making each random query, we show that the memory at that moment contains at most S over n bits of information about the next random query in average. Intuitively, this is because the next random query is uniformly random, and we only have S bits of of memory. Therefore, we can conclude that for the algorithm to learn the answer, which is yes or no, the algorithm needs to make at least n over S number of queries. So step 2 is formalized by a careful chain rule and information theoretic potential function that caps the number that the information learned each step. And in the real proof, we need to study the information gained by a block of random queries in a batch. And we use shears inequality to achieve this. So the next part is the PDBHP problem. This captures the indistinguishability between DTL and DTL plus 1. Given L blocks of random queries generated by the hidden partition P, is the next graph a yes graph or a no graph? That is it a noisy bipolar graph or a uniformly random graph? This can be formalized by as a two-party communication, a one-way communication game, where Alice is given as input a partition P and can send S bits of information about P to Bob. And Bob is given a block of random queries and needs to determine whether the random queries he received is from a yes or a no graph. So this problem is generated from the DBHP problem by Kaparlov, Kannan, and Sudan. The main difference is that in their setting, the block of random queries are very few. The length of the block is only sublinear in n in their case, and the graph is not noisy, which means that in their yes case, the graph is a complete bipolar graph. So their proof has two steps intuitively. The first shows that the support of random queries form a cycle with very low probability. This is because the length of each block is short. And this point is important because cycles can be used to distinguish yes and no cases easily. In a complete bipartite graph, a cycle must contain an even number of edges, while this is not necessarily true in a uniformly random graph. And conditioned on a cycle-free graph, they show that the distribution of Bob's yes input is close to uniform, conditioned on a typical message M. This is achieved by Fourier analysis. And typical messages here means the messages that Bob will send with probability above average. In our setting, there may be a lot of cycles because the length of each block is maybe very large. But we don't care about cycles anymore because the input graph is noisy. And in the second step, we show that the noisy but dense yes input to Bob is still close to uniform, conditioned on a typical M. Our proof in spirit follows the idea of KKS 15, but there are technical challenges arise in our settings that we skip here, such as those in bounding the Fourier coefficients. Lastly, we show the proof to result 3. We call that result 3 is a lower bound for recurring correlational clustering in a stronger model, where both adjacent matrix and adjacent list queries are allowed. This model is named general graph model and is introduced and studied in Kaufman, Krivelovich, and Ron. This is a clean mode of a natural mode of computation and is interesting in its own right. Specifically, in their work in KKR04, they showed that testing bipartiteness in the general graph model costs strictly less queries than in adjacent matrix and the adjacent list model. But the challenge is that showing lower bound in such a stronger model is also harder. An algorithm can know in only n queries the degree of all vertices, and given the degrees, edge queries are no more local. So to that end, we use a distribution that decorrelates different parts of the input. So specifically, we randomly partition the vertex. So here is the input distribution. We randomly partition the vertex set V into about 1 over epsilon groups of equal size, and we make each group a clique. For each pair of groups, we make their induced bipartite graph a sparse and regular bipartite graph. So intuitively, this graph is constructed in a way that each vertex has many redundant neighbors, and algorithms can learn nothing from the degrees of the vertices because the graph is a regular graph. And in addition, the correlation clustering is dominated by the planted clustering. So here is our proof sketch. So we first show that formally that the planted clustering dominates the answer. And we will lower bound in a relaxed problem where we're leaving the group where this belongs to for vertices required too many times. That means that for vertices whose group is still unknown, querying this vertex, the queries on this vertex are still relatively local because we don't know much neighbors about this vertex. And the last step is that we show after n over epsilon queries, only a small proportion of vertices will be revealed with high probability. And Therefore, the planned clustering still remains uncertain. So here are some open questions. First, can we prove tight lower bounds and improve results 2 and 3? And can our proof generalize to a wider range of time-space lower bounds for approximation problems? For example, those problems that are not cut related.